Hello. So we're going to be talking about transistor models for the BJT transistor. And before we do that, we've just talked about DC equivalent circuits and AC equivalent circuits, as well as how to decompose the signals into their DC components and AC components. And the reason why that's important is because the methodology that we're going to follow when we analyze or design transistor circuits is that first we're going to do the DC part of the analysis and then the AC part of the analysis for simplicity. So when we talk about transistor amplifier analysis or design, the first thing we're going to do is we're going to carry out the DC portion of our analysis, also referred to as the large signal analysis. And from that, we're going to get the DC values of our parameters, currents, voltages, and then we're going to draw the AC equivalent circuit and calculate the AC components of our signals, also referred to as a small signal analysis or design. Now, the reason for that terminology, large signal versus small signal, is simple. When we're talking about the DC portion, which represents the biasing or setting the Q point, we're going to be dealing with voltages in the range of volts and currents in the range of milliamps. Whereas when we talk about the AC analysis, we're typically going to be dealing with voltages in the range of millivolts and currents in the range of microamps. So that's the terminology, large signal versus small signal. So as I mentioned, the DC portion of the analysis is going to be biasing or setting the Q point. And the AC portion is where we're going to calculate the amplification parameters, the gain of the circuit, etc., input resistance, output resistance. And the reason for that is the signals that we're going to be amplifying are the small AC signals. Now, the transistor is it's a complex device. It's a nonlinear device. It has different regions of operation. And so it's going to be very difficult for us to analyze circuits using a mathematical equation for the transistor that takes into account all the different regions of operation and non-idealities and whatnot. And so we want to be able to do our analysis in a way that is simple as possible. And because of that, we're going to be using different models for the transistor in the DC portion of the analysis and the AC portion of the analysis. And those are going to be models that represent the behavior of the transistor, in one case for large DC signals and in the other case for small AC signals. And so for the DC portion, we're going to be using what we typically refer to as the large signal model of the transistor. And for the AC portion, the small signal model. And again, the transistor is the same. We're just, creating mathematical models of the behavior in a simple way. We're, in most cases, linearizing the behavior of the transistor over a specified region. So let's look at the large signal model. The most common large signal model is the Ebers-Moll model. And we've probably been using Ebers-Moll model already, except we've been using it in our head intuitively, where we say, we're going to approximate the base emitter junction as a forward bias PN junction, and so we're going to assume a 0.7 volt drop across that junction, approximately, and we're going to assume the collector current is equal to beta times the base current, and so there is a current control, current source, if you will, at the collector. So we've already created this model and used this model already in our head, but now we're going to put it on paper. I'm going to draw a small circuit so that we can see how the model will be connected or applied within a particular circuit. Let's just do a simple one where we have a transistor connected to VCC via a collector resistor, and then we have a base voltage connected to So this is our base DC source. So this is our circuit. So far so good, and now we're going to do the DC portion or the DC equivalent circuit. And as we do that, we're going to substitute the transistor or replace the transistor with its DC equivalent circuit. And we'll see in a second what that is. So first, let's go for that. So we're going to assume that the base to emitter junction is a forward bias diode. So this is our base. This is the emitter. Put this on the side so it doesn't. And then the collector current is equal to beta times the base current. So beta times IB, where IB is the current going into the base. Another thing to notice is that I'm using my DC signal representation, so capital letter, capital subscript. All right, so this is my Ebers-Moll model. It's very simple. And again, it's not that if you open the transistor, that's what you're going to find inside, but it's rather a mathematical model with elements that we know how to operate with, and they model pretty accurately the behavior of the transistor to large DC signals. And now we can connect the rest of the components. So there is a collector resistor, RC, that's connected between the collector terminal and a VCC supply. And then there is a base resistor, RB, which connects the base terminal to the VBB supply. That's my equivalent circuit. I'm going to highlight a little bit, a little box for my transistor. Oh, I forgot to connect the emitter, but I'll do that in a second. So this will be whatever is inside this box, that will be the large signal model of the transistor. And then we did forget to connect our emitter, which goes directly to ground. Within this circuit, things that we know just from the model is that the base emitter voltage is going to be around 0.7 volts, because we're assuming if we're in the linear region of operation, which is going to be the case when we are designing or analyzing amplifier circuits, it's forward biased. And then my IC current is equal to beta times IB, beta being the forward current gain. And then by Kirchhoff's current law, IE being equal to IC plus IB, or sum of the currents entering the device equals sum of the currents leaving the device. I haven't labeled IC and IE, but there they are. All right, and then once we are done with our DC analysis for our circuit, we will go into the AC analysis. And for that, we're going to use a different model, a model that best reflects the behavior of the transistor for small AC signals. And there are several models that we can use, but one of the most common ones, perhaps the most common one, is the hybrid pi model. So that's the first one we're going to see. So let's move on to small signal models. And I perhaps should characterize that and say these are small signal mid-band models. And I'm actually going to make that correction. And the reason for that is that these models are going to represent the behavior of the transistor within the mid-band region, meaning when we are talking about signals that are in the passband frequency of the transistor. When we're talking about frequency response in a later video, we're going to modify these models a bit to take into account the frequency effects. But for now, we're going to assume we are modeling the transistor in its passband, and so we're going to exclude some of those components for simplicity. So hybrid pi model will be the first one. And the hybrid pi model, it's going to represent the base emitter, just like, we talked about having a diode there. If you look at the behavior of a diode for AC signals, it resembles that of a resistor. How is that so? Well, we talk about, if you remember your we could call this IV versus VBE. It's going to look something like this. Same thing for IC versus VBE, except for different values in terms of current. But this is what it looks like. And so when we are looking at the IV versus VBE within a very small range around the Q point, let's imagine this is our Q point right there. So we are in the linear region of operation where there is a 0.7 volt drop across VBE. And now we're going to apply that small AC signal, which is going to make our signals, voltage and current, move around that Q point ever so slightly, because it's a small AC signal. It's just millivolts superimposed on top of that 0.7 volt Q point. And so this is what it's going to look like. I'm going to represent it in red. That's what that variation looks like. And you can see how it approximates, if the AC signal is small enough, if that variation is small enough, it approximates a straight line. And that will be the behavior of a resistor, a linear relationship between voltage and current. And so when we represent that for our AC model, we're going to represent that diode between the base and the emitter as a resistor. And then in the case of the collector to emitter terminal, we still have that current source, which we're going to represent with, or in terms of, the transconductance. And that's just for convenience. We could say, this is equal still to beta times IB, except, it will be beta times small IB now, because we're talking about the small AC signals. This is, we're going to call R pi. We're going to see in a second why. This is my collector. So this is the simplest form of my hybrid pi model, where we have ignored the output resistance of the transistor. We're going to complete the model in a second. But for now, let's look at where these things are coming from. So R pi, hopefully we've already seen why it makes sense. It's if we have a small AC signal, our diode behaves as a resistor. Beta times IB being the current now going into that base terminal, IC being current going into the collector terminal. We can also represent that beta IB as alpha times IE, so I'm going to say my collector current is equal to beta IB or alpha IE, where alpha, if we remember, is equal to beta over beta plus 1, so they're related. It's a number that's approximately equal to 1. And this is going to be equal to the transconductance times the input voltage, and the input voltage is going to be equal to the voltage from base to emitter, V pi. So transconductance, we're going to represent as GM, letter G for conductance, and V pi. Now, how does that work? Well, if we look at our relationship between current and input voltage being VBE, down here, I've represented the base current, but I could draw a similar curve for the collector current. It will have the same shape. The values of IC obviously will be different, will be beta times smaller than IB, but the general shape of the curve will be the same. Now the slope of this curve is equal to 1 over gm. We can also call the slope of that curve, we're going to call it little r for the resistance that's connected to the emitter. You may already have dealt with little r in the last, in electronics 1, a few videos ago, but we're going to call it little r, and that's just the resistance that we approximate as being connected to the emitter terminal. But you may say, well, but so why have we called that resistance r pi? And that's a good question. Why didn't we call it little r? And the reason for that is the resistance that we are seeing here is actually the resistance the diode resistance, if you will, from base to emitter, but we're looking from the base terminal. And if you remember, when we look from the base terminal through the transistor, what we're going to see as the resistance connected to the emitter is whatever resistance is there multiplied times a factor of beta. And so that's actually the relationship between r pi and little r. So maybe I can start writing some parameters here. AC parameters. And the first one that we're dealing with is GM, which is the small signal transconductance. That's why it's a lowercase, a small signal parameter. Then we have little r, which we just saw is equal to 1 over gm. And we have r pi, which is simply beta times little r. Okay, so it's just looking from the base terminal. We see that resistance multiplied times beta. And let's see if we can do some math here. So we have our expression for the collector currents. And I'm going to talk about large signal now, so let's just talk about the DC value. And we know that the value of the collector current, there is an exponential relationship between the collector current and VBE. And so we can approximate that as being equal to this small leakage or saturation current times E to VBE divided by VT, where VT is the thermal voltage, which we're going to approximate as 25 millivolts at room temperature. Now, this is only an approximation because there is a -1 term that we are omitting simply because in the linear region, the e to the VVE over VT is going to have a value that is much greater than 1. So we're going to omit the -1 term, which you may have seen when you studied diodes. And so our GM, if we look at the picture, is going to be the small delta, if you will, delta IC over delta VBE. So and so if we take the derivative of this expression with respect to VBE, what we will get is 1 over VT times the same function. That's the derivative of an exponential function. So times IS e to the VBE over VT. And we can see, if you look at that expression within the parenthesis there, it's just equal to IC that I just wrote. And so this is equal to IC divided by VT. Okay. So that will be the value of my small signal transconductance. Notice that the small signal transconductance is dependent on the DC current flowing through the collector, the DC collector current IC, as well as the thermal voltage, which is going to be a constant, only varying with temperature. So I'm going to write that up here. This is equal to VT divided by IC, which makes my little r equal to the inverse of that, right? IC divided by, oops, I did this backwards. Hold on. Conductance is current over voltage. Resistance is voltage over current. So this is the one that is IC over VT. This is VT over IC. And obviously R pi is just going to be beta times VT over IC, or beta times little r e. And this, this could be a pretty good model for many applications, but we're ignoring one of the effects. We're ignoring the early effect or the early voltage. If you recall, when we studied the IV curve for IC versus VCE, so we can call the one that I just drew, the first one will be the input IV curve, and this one is the output IV curve. It's the output current versus the output voltage. And we said we can draw it as something like this. And in here we are assuming that for a given Q point, let's imagine my Q point is right here. For a given Q point, my signal is going to vary like that around that Q point, right? We are assuming that the current is going to remain constant, independent of changes in VCE voltage. That's the approximation. And we saw when we studied second order effects of the transistor that there is actually a slight slope to this line. And so this will give you a resistance, an output resistance essentially of infinity, which is the ideal output resistance of an ideal current source. But if you represent the actual slope, let me modify those curves a little bit to take into consideration the early effect. It's probably not as, I'm exaggerating it a little bit, the slope is not that big typically, but let me mark my Q points. So my Q point is here. And now my small signal variation around that Q point is actually going to have a slope to it. And we call that the slope, or the inverse of that slope will be the output resistance of the current source. Why the inverse of that slope? Well, resistance has units of voltage over current, and you can see that this is actually output current over output voltage. So current over voltage gives us conductance. Let me see, black. I'm going to say here that the slope of this line is equal to 1 over little r-o. And I'm just saying that I sort of messed up in the previous one because I put, so let me correct that. This is not 1 over gm, but rather this is gm in this case, which is 1 over little r-e. I apologize for that, but just as in this case, we have units of current over voltage, so that is conductance. In this case, it's 1 over little r-o. Now, when we look at the expression for our IC current, we can say IS e to the VBE over VT. We can say, well, there's nothing there that shows a relationship between IC and VCE, and that's because we have not introduced the term with the early voltage. And so a more complete model would be 1 plus VCE over VA, VA being the early voltage. And so, just like before, we have that if 1 over little r-o is equal to delta IC over delta VCE, I just need to take the derivative of this function with respect to VCE. And with respect to VCE, it's going to be 1 over VA times IS e to the VBE over VT. So the whole IS e to the VBE over VT term in this case is going to be a constant because we're taking the derivative with respect to VCE. So we have a constant multiplying the function, and that's just going to be equal to that constant times the derivative of the function, which is 1 over VA in this case. And if we look at it, we can see that this is approximately equal to IC divided by VA. Again, we don't have the 1 plus VCE over VA term, and so we're considering this to be approximately equal to IC, but that's going to be a fairly accurate approximation, especially when we're talking about, that Q point only. Now, in the previous case, we also didn't take into consideration that factor of 1 plus VCE over VA, but we could have back here also said, oh, this is times, to be more precise, 1 plus VCE over the early voltage. And notice that will not have changed our results in the least bit. It will have meant that in this case, our derivative will be this multiplied times that constant 1 plus VCE over VA. The reason why it's a constant is because in this case we're taking the derivative with respect to VVE, not VCE. And this is still equal to IC divided by VT. Okay, now how do we represent this little RO, this output resistance that we just found the value of in our hybrid pi model? And that's simple. Going to move my collector terminal to make room for it, but it's just the resistance that appears across that output current source, little RO. So this is now my collector. This is my hybrid pi small signal model for the transistor. If I wanted to draw the equivalent circuit, the AC equivalent circuit, for my original circuit that I put there before, it will be something like this, RB. And in this case, I only drew a DC source up there, so this will just be tied to ground, because when we are doing the AC equivalent of a voltage source, we have to make the voltage across the terminals equal to 0, and we do that by shorting across the source. And likewise, on the other side, we have a collector resistor tied to a DC source, VCC, and the DC source becomes a short in the AC equivalent circuit. Then my emitter will be directly tied to ground. So this will be my equivalent circuit. There is one more thing. I haven't written the expression for little RO, but I will do so. And if 1 over little RO is IC divided by VA, then little RO will be VA divided by IC. So that's my hybrid pi model. There is one additional model that is sometimes useful to analyze, and that is the T model. And again, it's just a different way of representing the behavior of the transistor. I'm going to go ahead and do it right next to here. Maybe I should move my AC parameters somewhere else. Or I guess I'll just eliminate them. Hopefully you've taken note of them. But I'm going to draw that second model, which is the T model. This will be 1 and that will be 2. Now, the reason why we may use a different model is that in some cases the analysis of a circuit may become easier if you use a different model. And so you will see in most textbooks, they may use the hybrid pi model for some analysis or the T model for other analysis, and it just depends on what will be simpler to analyze in each particular case. So let's go ahead and draw it. It's very similar to the hybrid pi, obviously. You still are representing your collector terminal via current source. you're still representing your base to emitter connection as a resistor because of that forward junction that's gonna behave as a diode, and for small AC signals as a resistor. Now you're representing this as little Re because this is just the resistance that is truly connected to the resistor, not looking from the base. The base in this case is connected here. So again, notice in the hybrid pi model, that resistor R pi was the resistor from the base to the emitter, looking from the base into the emitter, whereas little R is the resistance, from the collector to the emitter. So it's not multiplied times a factor of beta just yet. So that's why it's little R as opposed to R pi. This is our voltage between base and emitter, V pi. This is beta IB, even though in the T model, it's more common to just say, alpha times IE. And that's it. If we wanted to represent the output resistance, we can also do so as little RO. And this will be our model of the transistor in this case. So I'm going to put the same box as before. And you will just make the pertinent connections. One more thing to notice, and I guess it's written here, when we are talking about transistors, we, as a first order approximation, we said we're going to consider it at least the BJT as a current gain device, meaning the collector current or output current is equal to beta times the input current, which is the base current. But a more general way of thinking about transistors, which applies both to BJT and MOSFET, and perhaps a more accurate way of looking at them, is as transconductance devices, where the input signal is actually a voltage and the output is a current. And in this case, that transconductance equation, or that relationship between input and output in terms of input voltage and output current, is represented here. Notice that we said IC equals GM, the small signal transconductance, times the input voltage V pi, which is none other than little VBE. I probably should have written that somewhere. So let's go ahead and let me write again the AC small signal parameters. And maybe I'll include that one this time. So we had GM being equal to IC over VT. We had R pi, or rather little r first, as being equal to 1 over GM. So VT over IC. R pi was equal to beta times little r. R out equal to VA over IC. And I'm going to write, V pi being equal to little VBE as our last parameter. And again, I'm going to typically represent my current source as VM times V pi, or little VBE. And the same thing here, GM times V pi. And that's it for the small signal models. Again, right now it may look a little complicated. Why would you go through the trouble of redrawing the circuits using these models? And in all reality, we're probably not going to always do it. Most of the time, we're just going to analyze the circuits in a more intuitive way without having to redraw the whole thing using the model. But what we're going to be keeping in mind in the back of our head is really the behavior of the model. And for more complex circuits, we may actually need to redraw the circuit, substituting the transistor with its model to get a more accurate or a simpler analysis. Anyway, that's it. Thank you.